So we were saying that if two babies were born and they lived for 5 years, then together they lived for 10 years. This is the idea we're behind here. We're trying to get is these 100,000 babies born, how many years did they live within the first interval? Now, the first interval length is 1 year. If all of them lived for 1 year, then obviously that will get you to 100,000 years. However, not all of them lived for 1 year. You can see that we have 1,008 that died. So for those that lived the entire period, we can all of them give them 1 year of life. And then for those that died, we can say, well, let's say we give them half of the interval. So how many actually lived the entire interval? Well, those that lived the entire interval actually exited the interval and entered the second interval. So 98,992 lived the entire interval. So every one of them, of those that exited, and therefore we can see them in the second interval, we're going to give each one of them the entire interval, which is 1 year. And for those that died, the 1008, we're going to give each one of them half a year. We add these two numbers together and you get the 99 1,093 years of life lived within the first interval. And you do the same thing for every interval. So second interval, 98,9992 entered, 204 died, and therefore 98,788 died. So for every one of the 98,788 that lived all through the interval, we're going to give them the entire interval. So we're going to give those 4 years. And for those that died, the 204, we're going to give them half of that. You add these two numbers together and you get this number over there. You keep doing that for all of them and you fill out the last column. Now, the trickiest one is going to be the last interval, okay? The last interval, you have 30,000 that entered, 30,000 died. How many years I'm going to give each one of them since I don't know how long they lived. I don't know exactly the number, but I think they ended up giving maybe like 7 years on average in this example. So you end up having this column, which is the number of years lived within that interval by those that lived in that interval. The next thing you're going to do is you're going to do accumulation of the years lived from that interval on. So to be able to do that, to calculate how many years were lived in that interval and in subsequent intervals, you have to sum up the intervals backward. So you start on the bottom, the 21,000, and you start going backward. So 21,000, you add then 190,000, you get 391,000. Then you add the 264,000, you get 655,000, and you keep doing that till you reach the the bottom or the top, I mean, and that's 7.5 million years. And that, what this number mean, it means these 100,000 babies that were hypothetically born, cumulatively they lived for 7.5 million years. And therefore, if you take the 7.5 million years, you divide that by the number of babies, you get 75 years. And that would be your expected life at birth in the US in 1987. Okay, so I hope this helps. Um, Again, you need more detail. You can see the video that I made specifically for the calculation of the life expectancy. Now, the great thing about life expectancy is that you can actually compare countries, and since it's built using the age-specific death rates, then it accounts for the age-specific death rates, and therefore you don't need to do any adjustment. You don't need to do any correction. You can just compare them and say, well, in this country, people are expected to live longer than in other country. Also, if you have this table, if you go, for example, in 1987 and you ask yourself how many additional years people that were 40 to 44 in 1987 in the US are expected to live further. Well, you just go to 4044 and that will give you 37.7. Therefore, you can say, well, they're expected to live for an additional 37.7 years. All right. The next, and this is the last thing for this lecture, is we're going to talk about the adjustment. So I've hinted about it many times. So sometimes we need to adjust values because we cannot just compare values. It doesn't work. and we're going to specifically look at how do we adjust death rates, and specifically the age-specific death rates. And to do that, I'm going to use an example of two countries. One is Panama, the other one is Sweden, and they're picked specifically like that because Panama is considered a developing country, whereas Sweden is considered a developed country, and therefore you expect Sweden to have a much better public health situation than Panama, and which is true. Even though this was done maybe a few years ago, it's probably still true. Now, here's what happened. If you calculate the crude death rate of Panama, you will find it to be 9.3 per thousand, versus if you calculate that of Sweden, you will find it to be 10.2 per thousand. So if you stop here, you would say, well, there's more people dying in Sweden per thousand versus in Panama. So that makes you think maybe Panama has a better health system, which is not true. Sweden has a better health system. To help us understand what is happening, we're going to look at something called the age pyramid, which you probably have seen previously. So this is the age pyramid year 2000. So that's the year we're looking at. This year 2000, 20 years ago. Panama versus Sweden. And so if you've never seen an age pyramid, but I think you've already, what you have in the middle are the age categories, and on either side you have the number of population, male versus female, and that's true for both Panama and Sweden. And the idea is, for a country like Panama, you have a shape that looks like a pyramid, and basically what that means is that on the bottom, you have a very large proportion of the population, whereas on the top, you have a smaller proportion of population, meaning that the Panamese population is a younger population. The majority of the Panamese population are below the age of 30, so they are young. And obviously, young people, as we've seen when we looked at the distribution, the J-shaped distribution of death rates, they have a lower risk of dying. Versus in Panama, you have more of a barrel-shaped age distribution, and meaning that you have more of the population is older. So a high proportion of the population is within their 50s, 60s, 70s, and 80s, and since they're older, then they have a higher risk of death, and that's pretty normal. So here's what's going to happen. It is clear that Sweden has a larger proportion of its population in the older groups, and we know that the age-specific death rates of older people is higher than that of the younger one. So what we're going to do on the next slide is I'm going to show you the age distribution of Sweden and Panama. And also I'm going to look at the age-specific death rate for both countries. Okay, so here it is. I have a table. Again, on the first column are the age groups. So 0 to 4, 5 to 9, 10 to 14, all the way to 80 plus. You have first Panama, next to it you have Sweden, and the values that I'm showing is the number of population per thousand. So this is 280,000, 300,000, etc., all the way to the last, which is I think 2,900,000. So the Panamese population is about 2,900,000 versus Sweden. If you look, it's 480,000, 620,000, all the way to the end. So the Sweden population was about 8,280,000. And then I've calculated the percentages of the total population. So those ages 0 to 4 represent 9.7% in the Panamese population versus 5.4% in the Sweden population. So children or babies are more prevalent in Panama versus Sweden. Next is 5 to 9, 10.3% in Panama, 7.5% in Sweden. And you can go on and you will notice that the situation is going to be the same all the way to the age of 30 to 34. Yani all the way up to the age 34, a high proportion in Panama are in that age group compared to Sweden. Then when you start hitting the age 35 and above, you're going to see the opposite, meaning that a high proportion of the Sweden population is in that age group versus the Panamese. So 7.5 versus 6.9, 7.2, all the way till the end. So this slide is saying what we already said is in Panama, a high proportion of the population are aged below 35, whereas for Sweden, it's a high proportion that are above that age. So you can look, for example, 60 to 64, only 2.8% of the Panamese are 60 to 64 versus about 5% of the Sweden population. So that's the first key in this setup. Next, what we're going to do is we're going to compare the age-specific death rate between the two countries. Okay, so again, we have the exact same age groupings. Sorry, 0 to 4, 5 to 9. This is the same. Again, the age, the population distribution, nothing changed for Panama, nothing changed for Sweden. What you have new here is the age-specific death rate for Panama and the age-specific death rate for Sweden. What I want you to notice is the following. Pick any age group, compare the two, and you will find that it's higher for Panama. Yani, among 0 to 4, it's 5.1 per thousand for Panama, where it's only 2.1 for Sweden. And obviously, lower risk of dying in Sweden for that age group. Type 5 to 9, 4.3 per thousand for Panama, 1.2 for Sweden. Again, a high risk of death in Panama. For, let's say, 30 to 34, it's 8.3 per thousand in Panama compared to only 4.8 Sweden. Type, what about 60 to 64? 20.4 per thousand in Panama versus 16.4 in Sweden. Again, pick any age group, you will see it's always higher in Panama, meaning that the death rate specific to age group is always higher in Panama than in Sweden. However, if you ignore the age distribution, if you just add them all together up, you're going to see the opposite. And this is how it happens. So here I'm calculating the number of deaths in Panama. How I do it? It's very simple. You have the population size, you have the age-specific death rate, you just multiply these two numbers together, you get the number of deaths for that age group. So based on the fact that the age-specific death rate is 5.1 per thousand, I'm sorry, so for every 1,000 I expect 5 to die in that age group, I have 280,000, and therefore I multiply these two numbers together. I figure that I have 1,428 dying in Panama in that age group. I do the same for Sweden. It's 2 per 1,000, and I have 480,000. I multiply these together. I get 1,000 deaths in Sweden for that age group. And I do that for every age group for both countries. And at the end, you have the total number of deaths in Panama and the total number of deaths in Sweden. You have the total population size in Panama, the total population size in Sweden. And sure enough, if you divide the total number of deaths by the total population, that will give you the crude death rate for Panama and the crude death rate for Sweden. And sure enough, what you will see is a lower value in Panama versus Sweden. I hope you realize the the um, uh, the paradox that just happened. The paradox is that if you compare every age group, Panama will always be lower, 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 lower. However, when you look at the total, it's higher in it's always higher in Panama. For every age group, the age-specific death rate is higher in Panama. Yet, if you do the total, all of a sudden it's lower. This is because of the age distribution. It's like a simple way to do it. You're comparing two students. One student has a better grades in biology and chemistry, in pharmacology, in all the courses they have better. But yet, when you do the overall GPA, the overall GPA is lower than the other student. It doesn't make sense, right? It doesn't make sense. And this is because of the age distribution. So the way to correct that is we need to do something with the age distribution. Okay? So from the previous tables, it's clear that the age distribution between the two countries is different. Within each age group, the age-specific death rate for Panama is higher. Nonetheless, the crude death rate for Panama is lower. Thus, we need to account for the age distribution between the two age group. So we need to do something. These two countries have um, different age distribution, and therefore, when you do the crude death rate, it's not fair. So to compare, to control or to adjust for the age distribution, there are two methods: Vienna direct method and the indirect method. And basically, the direct method and the indirect method, what you're doing is one of two things. There's nothing else you can do. Either you have to change the shape of one of the populations so that its age distribution will look like the other, and then you calculate the age distribution, the death rates, and therefore, since you made them similar with regard to their age distribution, then you can compare. So one thing you do is you fix the age distribution, you make it as if the two countries have the same age distribution, you solve the problem, or you make them as if they have the same age specific death rate. So you keep the age distribution, you don't touch it, you make them as if they have the same age specific death rate, and then you compare. So let's look at how this works. We're going to start. So one method is called the direct method, the other one is called the indirect method. The direct method, let's suppose the age distribution of Panama was the same of Sweden, meaning we will select the age distribution of Sweden as the standard one. I think what epidemiologists and public health do is that there is a standard age by gender distribution, if I'm not mistaken, and that could be like a good work for you to look it up. By the WHO, they have a standard population distribution, and all countries adjust their death rate to that population, so that all countries in the world, they have theoretically the same age and gender distribution. However, they keep their own age-specific death rate and therefore calculating an overall adjusted death rates. If you did not understand, that's fine. We're going to look at the example. So here what we're going to do is we're going to consider Sweden to be the model age distribution, and we're gonna squeeze the age shape of Panama so that it looks like that of Sweden. And once we do that, we recalculate the number of deaths and we recalculate the death rate. Okay, so basically that's what we're doing. We're taking Panama and we're forcing Panama to look like Sweden. Okay, so again, you've seen this before. These are the age group. This is Panama originally, how it looked like originally. Okay. Remember I told you Panama had 2.9 million. This is how Sweden looks like. And remember I told you Sweden had 8.3 millions. So what I'm going to do is I'm going to change the distribution of Panama to look like Sweden. So what I do is I take the total population in Panama and I multiply it by the percentage of Sweden to get the values for Panama so that Panama starts looking more like Sweden. Okay, so instead of having 280,000 in that age group, now I'm going to have 168,000 in that age group. And I do the same for the second age group. So again, 2.9 million divided by 7.5%, that's 217,000. And I do that for all, meaning that I've redistributed the 2.9 million. Okay, this is called the redistribution of the Panamese population to start looking like the Sweden population. Okay, so once you've done that, you're going to get the adjusted population. Remember a minute ago I showed you it was 168, 217. So you redistribute the population. The total is not going to change. The total is going to remain 2.9 million, but now the shape of the population is no longer a pyramid. Now it's a barrel, so it resembles that of Sweden. Now you're going to take back the age-specific death rate of Panama. These are the ones of Panama. I haven't touched them. You can go back a few slides and check that. And now I'm going to calculate the number of deaths that should occur if Panama had the same population distribution as Sweden. So if Panama, instead of having 280,000 in 0 to 4, it had 168,000, using the same age specific death rate, we would expect to see 857 deaths. And we do that for every age group, and you end up with a total death of about 38,000. Okay? And then you say, okay, the unadjusted number of deaths in Panama was 27,000. Once I adjusted the age distribution of Panama to look like that of Sweden, the adjusted number of deaths is about 38,000, and therefore 38,000 divided by the 2.9 million is 13.1, and this is your adjusted death rate. Now I can compare this 13.1 to Panama because that value has been adjusted for the age distribution of Sweden, I'm sorry, and therefore the two countries can be compared. The two countries can be compared because both of them now have the same age distribution. Every country kept its own age-specific death rate, and therefore the total death rate that you calculate now can be comparable. And obviously, once you've adjusted that, you notice that the adjusted death rate of Panama is higher than Sweden, which is what we were expecting to see. Okay, now this works only to compare Panama to Sweden because I changed the age distribution of Panama to look like Sweden. However, if I want to compare a lot of countries, as I told you previously, I think WHO has like a mock population distribution that all the countries in the world, they change their population to look like this one so that they can calculate the age by gender uh, adjustment, and therefore once they 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 uh, they calculated this number, they can compare one another. Okay, so this is called the direct method. Now the indirect method, we're going to keep the age distribution. However, we're going to adopt the age specific death rate of one country to another country. Okay, so again, I have this table, the age group, you're used to them, the population distribution of Panama, you're used to them, but now I've borrowed the age-specific death rates from Sweden, which is 2.1 for the first age group, 1.2, etc. And now I'm calculating again the number of people that I would expect to see dying in Panama if Panama had the same age-specific death rate as Sweden. You do that for all the age group, you get a total of 19,000. So the observed number of death was 27,000. The expected number of death is 19, and therefore we talk about something called the standardized mortality ratio, which is the observed divided by the expected. So you put the 27,000 over the 19,000, you get 1.4. Okay, meaning the observed is higher than the expected, and therefore Panama, we have more death than expected. Expected based on what? Expected if Panama had the same age-specific death rate than Sweden. Okay, so the observed mortality is 1.4 higher than expected if Panama had the same age-specific death rate than Sweden. Since it's greater than 1, then what that means is that there was more death in Panama than expected, and therefore there's a higher mortality in Panama than in Sweden. If I did the opposite, if I took the population of Sweden as it is here and multiplied it by the age-specific death rate of Panama, then the expected would be higher than the observed, and therefore the standard mortality ratio would be less than 1, and therefore you would say that you're observing less death than expected if Sweden had the same age-specific death rate in Panama, and therefore you would reach the exact same conclusion, which is there is higher mortality in Panama than in Sweden. So here's we have an example of population health indicators. Um, Life expectancy. This is United States versus Mexico. It's done for men versus women separately. Usually, whenever you see something like that, you have to look at what year this is. It should be showing somewhere. I can't say it, but uh, it should have been there. So you can see that the life expectancy for men in the U.S. was 75 versus 73 in Mexico. For women, it's 80 versus 77 in Mexico. The mortality rate per 100,000, and here you have a note. That note says that mortality rate is for the standardized population, which means the population have the same age distribution, meaning it has been adjusted for the age distribution. These are not crude, these are adjusted, and therefore both US and Mexico have been modeled to look like the standard population, and you end up with 623 deaths per 100,000 for the men in the US compared to 742 in Mexico. It's higher in Mexico, and therefore you can conclude that there is more mortality in Mexico. Maternal mortality rate per 100,000 lives, 14 in the US, 83 in Mexico. You can see how much higher it's in Mexico, much, much higher. As I told you, maternal mortality is a very important indicator. Infant mortality rate, again, per 1,000 live births, 6.8 in the US versus 15 in Mexico, almost the double. And by the way, the US doesn't have the best indicators. You can look it up online. You can see that there are countries with much, much better indicators. Cause of death for children under the age of 5 for diarrhea and pneumonia, you can see very, very low in the US, but that's much higher in Mexico. Obesity and diabetes. Obesity, on the other hand, higher in the US than in Mexico, whereas for diabetes, so this is, I think it's like a prevalent rate. It's about the same. Amma incidence, you have here incidence for infectious diseases for tuberculosis. The incidence, remember, these are the new cases, 5.8 per 100,000 in the US versus 16, almost triple in Mexico. Okay, so I hope this kind of give you an idea of how you can compare countries when it comes to health indicators. Last but not least is where do we get the data? To get the data for these things, we go to the Census Bureau, we go to the vital statistics, where records of birth and death are kept, morbidity data, مثلا registries, and linked health records. Well, that would be a very advanced setup, which I think in some of the Gulf countries they already have that. That's it for this lecture. So that lecture overall covered the health indicators, whether they're mortality or morbidity, the different types, different calculations, and how they can be used to compare between countries.